Good afternoon and welcome to MAE 209. My name is Richard Kohar and this is Lecture 5, Elementary Combinatorics in Probability. I hope you can hear the audio very clearly. If so, give a thumbs up in the chat. Perfect, thanks. Okay, well, without further ado, here we go. So we talked about the this proposition, which is what we'll call the complement rule. That's kind of where the last thing that we had talked about. So here's the complement rule. And we ran out of time. So next we're going to talk about is what we call the principle of inclusion and exclusion. So the idea is that we want to know what, say, the probability of A union B is. So I have this here. And what I need to do is I need to sum up the probability of A plus the probability of B. Okay, but if I do that, and let me just grab a pencil in this case. So here's one eraser. So if I sum up everything in A, so what I do is I'm going to have everything in A. I'm going to put a mark here. And then I also will have the probability of B, so I will have everything in this section and this section as well. So what I've done is I've effectively double counted the intersection. So to do that, I'm just going to subtract the intersection, so A intersect B. So by doing that, I effectively can remove one of the marks. And so I just have 1, 1, 1 everywhere, okay? So I just will write some of the words over on this side. So the probability of the union of two sets is equal to the sum of the individual probabilities minus I'm going to call it the two-way intersection. Okay, so that's what it is in words. So here's a picture, here's the formula, and here it is in words. So let's do an example. So we have in a city, let's say in Kingston, 60% of the households have fiber internet, 80% of households have fiber TV, 50% have both services. If a house is randomly selected, what is the probability that it gets at least one of the two services from Bell? So what this effectively is asking for is, what is the probability of either internet or TV or both? So that's at least one there. So with this, internet union TV, that's equal to the probability of the internet plus the probability of TV minus the intersection of both. Okay, so we have 0.6 plus 0.8 minus 0.5. So you have 0.6 plus 0.8, that gives you 1.4, and then you subtract the 5, that should give you 0.9. Good. Yes, and I see in the chat 90%. Yes. So that's the probability that at least 2 of them will have Bell. It's 90%. And what is the probability that it gets exactly one of these services? It might be easier to fill out a Venn diagram at this point. So I have the overlapping services. This is 0.5. So let's say 0.5 here. And over here, I have, let's say 5 TV, there's 80. So minus, 0.8 minus 0.5 gives you 0.3. And then you'll have 0.6 minus 0.5, so that gives you 0.1. So again, the probability that it gets exactly one of these services from Bell is 0.1 plus 0.3, so that's 0.4. Yes, 5 is Bell. Yep. So that's from the Venn diagram. It's 40% of households. Have exactly one service. Okay, can you quickly go over why you subtracted them? So we had explained here that one way of thinking about this is that where did the 0.1 and the 0.3 come from? Okay, so so 50% of households have both services, so it goes in the intersection between the internet and TV. So in this area here, the 0.5 represents both services. Now, 60% of households have internet, so 0.1 plus 0.5 will give me 60%. And also the 0.5 and the 0.3, that sums up to give you 0.8, or represents 80% of the TV users. So does that answer the question about where the 0.1 and 0.3 come from? Again, we're looking at the entire set of TV. In this case, like TV is right here. So that would include the 0.5 and the 0.3. So again, that sums up to give you 0.8. Okay. As for why there's why we subtracted here, again, we are trying to avoid overcounting. So if I sum up all of the area or the probability, there's all the probability in A. So if I sum that up, I get all that area. If I sum up then all the stuff in B, there we go. But notice that I've double counted now this intersection. I've got it crisscrossed here. So I have to subtract that intersection. Okay? And that's why. Why can't we use the same method? Why don't we use the same method for the first question? I'm not quite understanding. We do right here. So for part A, this is what is the probability that it gets at least one of the 2 services from Bell. And so that is equivalent to us saying that it's you can have internet or TV or both. And so there it is. And we can use the formula that we had up here. I'm just replacing A with internet and B with TV. And so it's the probability of the probability of internet plus the TV minus the intersection of both. And so that's where we get 0.9. So then a bonus question is, C, follow-up, which is, what is the probability that the randomly selected household has none of those services. So what is the probability that the randomly selected household has none of those services? What do you think in the chat? 10%. Yep. And the way that we would do that is we would say probability of no services is equal to, and so what we're going to use is the complement rule. So again, very similar to what we did here. They don't have all the same coffee. We just take 1 minus the complement. So in this case, it's the probability of no services. Then I do 1 minus at least one service. But we already know that that's equivalent to us saying that it's the internet union TV, which is 1 minus 0.9, which equals 0.1. Okay, good. Any questions about that? Okay. Then starting the set for lecture 5, we have the principle of inclusion and exclusion, and that's for 3 sets. So for 3 sets, I want the probability that it's A union B union C. Okay. So in this case, we sum up all the probabilities in all the sets. So A, B plus C. Okay. So this is what happens. I'm going to put a mark here, 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 here. Oops. This is why I need to be very careful about counting. So I'm going to look at all of A. So it's going to be, we're going to look at all those regions here. So I've marked all the regions here that are covered by A. The next one is I have all the regions I need for B. So it's here, 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 and here. And then for C, I have here, 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 and here. So you can see I've doubled and sometimes even triple counted at this point. So what I'm going to do is I'm going to subtract the intersections. So A intersect B A intersect C, and subtract N, sorry, I should be using P. Because we're talking about probabilities here. So here's the probabilities. And then, so B intersects C. So what that ends up happening is that I will eliminate this one, this one, this one. And then I intersect this one and this one. So what ends up happening is that I get a mark here. So I've removed all those, but now I'm left with nothing in the three-way intersection. So I need to add that back in. Plus the probability of the three intersection. Okay. So what that means in the paper didn't soak the ink fast enough. Okay. So anyways, sorry about that. The probability of the union of three sets is equal to, so it's the sum of the individual probabilities, sum of the individual probabilities very similar to what we did last time, so we do minus we have minus, so minus the two-way intersections plus, maybe I'll use green. So plus, and we'll add that back in the three-way. Okay. So there is a pattern that starts to form. So you'll have minus the two-way plus the three-way for so for the probability of, okay, I'll use A1 union A2 dot 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 all the way up to AN. So I'm using n finite sets. So it's equal to the sum of the individual probabilities, so from 1 to n, of the probability of each of those. But then I need to subtract the two-way intersections. So don't worry about so much about what I'm putting down for the indices here. I'm just being rigorous, but just look at that as the sum of the individual probabilities, subtracting the two-way intersection probabilities, plus, maybe I won't bother writing down the, just to not scare people. Okay. Dot, and so that goes on and on till the very end. So n minus 1. And then that's the probability of a 1 union all the way to a n. So again, this may look like a very scary, daunting formula, but this is why I've been writing it out in words all along here. So again, if I wrote it out in words, it's just the probability of the union of n sets is equal to the sum of the individual probabilities Then we would subtract, so minus the two-way intersections plus the three-way intersection minus the four-way and so on and so forth. Okay? So as long as you just see that it's just alternating between minus and plus, that will help you remember it. I'm just waiting for the stream to catch up. If there's any questions, again, feel free to put them in the chat while I just kind of wait for the lag. Okay. So when the number of sample points is small, it is easy to count them. Okay, so if I let n, and the dot is just kind of a holder, so I could have, like, say I have n and it's like n of a. So n, and you have something inside of it, denotes the number of elements or sample points in a set or event. And then I let a be an event, so the probability, again, if this is a uniform sample space, again, and uniform meaning that each outcome is equally likely, then all you have to do is count the number of elements in A and divide by the total number of elements in the entire sample space. Okay. So what we're going to do then is we're going to get into what we call combinatorics. Combinatorics is the branch of math that's concerned with counting. Now, again, like I was saying, if it's a small number, it's very easy to count them one by one. But when things get into the tens, the hundreds, the thousands, the millions of possibilities, counting them brute force can take a little too much time. We can't list everything and we can't count everything. So we come up with clever ways of counting. And here's one of those techniques. So this is called the product rule for ordered pairs. This is from the textbook. So they have for two sets, if the first element or the object of an ordered pair can be selected in n1 ways, and for each of those n1 ways, the second element or the object of the pair can be selected in two ways, then the number of pairs is multiplied so that we have n1 times n2. And so what I like to think of that is there's n1 ways to pick from the first set, and then I'm going to pick from the n2, there's n2 ways to pick from the second set. So here's my example that, again, is different from the textbook. Not different in concept, just to give you a different variety. I have here a MacBook Air 2021, and let's say that there's two things here. There's storage and keyboard, and there's 256 gigabytes and 512 gigabytes for storage, and for a keyboard you can have English, German, and French. So instead of doing this, okay, so one way we could do it is you can make like a table. So you can have, here's 256, here's 512. Over here is English, German, and French. And so they start talking about ordered pairs. You can think of it as, here's 256, and then they pick English. You can have 256, then German, 256 in French, and the same thing for the 512. So we can see that there's 1, 2, 3, 4, 5, 6. 6 options for ordering the MacBook Air. Or the other way we could have done it is that there was 2 times 3. So there is 2 times 3 options, which gives us 6. 6 ways to order the Mac. Okay, so then in general, this is for KTuples. So if I had a pair here, here's 1, 2, that's an example of a pair. Over here, I have a triple or a 3 tuple. There's 3 of them in there. These are examples. These are just random numbers just to show you. And when we say a KTuple, there's k number of elements inside of there. Okay, so suppose a set consists of ordered collections of k-tuples, something like that, and that there are n1 possible choices for the first element. For each choice of this first element, there are n2 possible choices for the second element, and so on and so forth until you get to the end. For each choice of the first k-1 elements, there are nk possible choices of the kth element. Then what you do, so what they're trying to say here is that n1 isn't going to really affect n2, and n2 isn't going to affect n3, and so on and so forth, all the way up to nk. If you can do that, then you can just multiply the number of ways for each of those. So n1 times n2, all the way up to nk, and that's the possible number of k-tuples. So if I extend that example that we were using with the MacBook Air 2021, again, there's 2 options for the storage. So I could pick the 256 or the 512, so there's 2 options for this. There's 3 options for the keyboard. And next, there's 2 options for the memory. So there's our storage. Over here is the keyboard, so the number of choices, and over here was the memory. So 2 times 3 is 6, times 12, times 2 is 12. So there's 12 ways to order Okay, so that's fairly straightforward if you're just multiplying them together. So you use the product rule if your previous choice doesn't affect your next choice. If your previous choice does affect your next choice, you may want to consider a tree diagram. So over here, this would be an example of where you can't use your product principle or your product for pairs or for your K-tuples. So consider this experiment. You're going to be assigned to a vehicle, and you're going to be whoever is going to assign you the vehicle, they're going to say they're going to flip a coin. If it's heads, then you will pick randomly from amongst 5 working and 4 non-working ATVs. If it comes up tails, you'll pick randomly from among 6 working tanks. How many sample points or possible outcomes are there? So this is where I would consider using a tree diagram. So I would say here I would have 2. So in this case, I would flip a coin, so this would become either heads or tails. Then over here, if it's heads, you will pick randomly among the 5 working and non-working ATVs. So there's 2 outcomes for this. You can either have, let's say, W and W prime, so for not working. And then over here, this is working. Or maybe I'll call this is an ATV. This is a non-working ATV. So, and over here, maybe I'll call it just something different, X. So you can see how many sample points there are. There's 1, 2, 3. Because my sample points here is I can have it heads or working. I can have heads not working, or I can have tails and you have a tank. So in this case, there are 3 outcomes. Or I can also say or sample points. Good. This is something not mentioned in the textbook, but as I'm going to say, it is still incredibly useful to point out. This is the sum principle, and this is what I call the OR. So with the product rule or the product principle, I call that the and for this one I call it the OR. So with this one, if there are n1 choices for the first action and n2 choices for another action, then these two these 2 actions cannot be done at the same time. Then there's n1 ways to pick from the first set, or there's n2 ways to pick from the second set to be one of these actions. Okay, we can extend that for more actions, so n1 plus n2 all the way up. So as an example here, there are 3 action movies, 4 comedies, and 2 science fiction films playing at the Landmark Cinema in Kingston. How many choices do we have to watch? How many for which movie to watch? Nine. Okay. Yep, exactly. So there's 3 plus 4 plus 2. So that gives you 9. Okay, perfect. So, some more notation to introduce. What page are we on? We're on page 6 now. So let's go through some what we call factorial notation. Now, there's something in mathematics where, let's say I have 9 times 8 times 7 times 6, all the way down to 1. So I'm multiplying all the numbers from 1 to 9. This can be quite tedious to write out all the time. And mathematicians have a quick way of doing this, that if it starts at 9 and goes all the way down to 1, well, we just write that as 9, and we put an exclamation point. So this is read as 9 factorial. It's not like we scream 9. It's a notation. So that's what it means. We can use it one more time. Let's say like I have 10 times 9 factorial. Well, that's 10 times, well, I know what the 9 factorial is up here. So I'll just move it over by, I'll just write 362,880, and because of the 10, I'll add an extra 0. So we're done. So I can use previous calculated factorials. I can multiply together. The other thing too is if I had, let's say I had 10 times 9. So again, very tedious to write all this out. Could I call it 10 factorial? Ooh, that's very good. Yes, you can. Yes, you can. So again, it's very tedious. You can see that these cancel out, each of those numbers. The 9s cancel with each other, the 8s, the 7s, the 6s, there's the 5s, the 4s, the 3s, the 2s, and the 1s. Now that would equal just 10. But I could have also written as 10 factorial over 9 factorial. Okay. And what I can also do then is doing similar to what I did up here. I can expand that out, so I could write that as 10 times 9 factorial all over 9 factorial. And so those 9 factorials cancel, leaving me with 10. So let me just give you the definition then of factorial. So if I have n factorial, and it's going to start at the top number and it decreases by 1 as we multiply each of them, all the way to 3 times 2 times 1. And so that's if n is greater than 0. It's 1 if n equals 0. And n is an element of the whole numbers. Those are called the whole numbers. Okay, so we have that. Maybe that's important enough to box. Oof, hopefully I don't smear the ink. There we go. Okay. So what we can do then is something big like 70 factorial cannot be done by some calculators. So it does help to be able to simplify. So I'm just basically doing some examples here. Here's A, here's B. This one I'm going to do 67. So I can write that out. I'm going to write 70 times 69 times 68 times 67 factorial. I have 67 factorial on the bottom. I can cancel those out. So I'm left with 70 times 69 times 68. And that equals 328,440. Now again, mathematicians are looking for something quicker to write. So, yep, that's a good thing to point out. Excellent. But there's still, we get numbers like 70 times 69 times 68. This takes a little bit time to write. So what they have come up with is we would write this as P, and we would say that there's length of 3, so there's 3 of them, and it starts at 70. And what does the P stand for? It stands for permutation. Now we're going to talk about that in a moment, but it stands for permutation. And so the definition of that is that if I have P, I have K sub n, that's equal to n times n minus 1, n minus 2, all the way to n minus k minus 2 times n minus k minus 1. But as long as you can remember that this means it's going to be 3 numbers, and it starts at 70, you'll be able to reconstruct that. And so we can also come up with a different formula for this. That PKN is equal to n factorial over n minus k factorial. So that's another formula right there. Oops. And you can see that this formula works. Here's my example. So if I used P3, 70, which we had done up there, using this, this tells us it's going to be 70 factorial over 70 minus 3 factorial, which gives us 70 minus 3 is 67. And basically what we're doing is we're rewriting what we had up there on the previous page. And so this is just a quick way of being able to write that out. Okay? So this is what we call factorial notation when we use the exclamation point. It's n factorial. And then we also have this one, which we call permutation. That's, I would say n permute k, but this is very different notation in this textbook. There's no universal notation when it comes to permutations. So what we have here is permutations versus combinations. So over here, I have a permutation. Here's a combination. And the idea is that the order matters. And over here, the order doesn't matter. So things like over here, where we would say we would have cadets lining up for a photo, or we could have somebody, let's say that we're going to start giving out positions, like this is the president, here's the VP, here's the secretary, the treasurer, and let's say that this is some sort of liaison. So again, if I change the order, if I had put orange in this position and the green in this position, if I change the order, then basically what I've done is I've created a new committee. Where over here, the combination, I don't really have any labels for them. I don't really care in which position that they are. So this is where what we call a combination. It's where the order doesn't matter. So over here, we have a permutation is an ordered subset. The number of permutation of size k that can be formed from the n individuals or objects in a group will be denoted by p, and then it's k, comma n. So over here, there are 25 cadets who form a club. In how many ways can a president, a VP, and a treasurer be selected? Well, you would have 25 choices for the president. You would have 24 choices because one of them has been selected for the president. And then for the treasurer, there would be 23 because you've picked 2 now for the president and the VP. So here's the treasurer. So what that works out to is that it's P, and so you would have 3 comma 25. Yes, it is. Thank you everyone for tuning in. I appreciate all the questions in the chat. If you have any more questions, feel free to send me an email. Until next time on Thursday, keep working on it and take care. Have a good day, everyone. Bye.